fold. One roadmap is dedicated to Mars. So certainly one aspect or main aspect is that collisions on Mars can generate dust, which can go into the atmosphere. You can have fragmentation collisions, aggregation and all this stuff. And that is important for understanding the processes in the Martian atmosphere. This is certainly something which is a bit overrated. We all know that, but I still think that kind of gets the point to get particles into the atmosphere and understand something about them if we deal with collisions. The second motivation is that I'm also doing planet formation. Shall I wait? No problem. Planet formation. So here it's not the Martian atmosphere, but it's a protoplanetary disk. So solar system size where planets form. And I think a couple of you here do also Venus atmospheres, Mars atmosphere. So in principle, a protoplanetary disk is nothing which is so different from an atmosphere. You have the same processes, particles move, collide, grow. So these processes sometimes kind of overlap. Sometimes it's more extreme in one environment than in the other. Physics is a bit different, but still sometimes it goes together. Okay, so let's talk about collisions. And since I thought this was supposed to be some kind of lecture, let me start very basically. Probably you all remember your first year classes in physics with collisions, having these gliders on air cushion tracks so that you don't have any friction and having them collide with each other to get the energy and momentum balances correct. And essentially what you find out then is two things. Either you have an elastic collision, so energy is conserved, or you have an inelastic collisions. And at these early times, I was thinking, okay, that's it. I understand everything about collisions. Obviously, there's more to it, but let's start with the easy one, elastic collisions. So just two particles bouncing off each other. That might not be very exciting because nothing much happens, just the velocities change a bit before and after the collision. However, this, for example, is something which is a problem in planet formation. Once your particles are millimeter size or so and start bouncing off each other, they don't grow anymore. And that's bad if you want to make planets. On the other side, if you always have bouncing collisions, you can, for example, tribocharge your grains and deal a lot with charges and these things. Now, if you go to the more interesting thing, something a bit more dissipative, that's actually usually not used in the first semester classes because that's already too complex, then because you could introduce something like a coefficient of restitution or so. But it's easier if it's either completely sticking or not. Anyway, you have something which is dissipated. So that is, for example, important if you have a granular gas, which is not driven by anything external or so. And then these things would, for example, lead to the cooling of this gas until eventually the energy is gone. Or it would be important for something like Saturn ring particles, which kind of remember their earlier collisions. So if you slow things down, they stay so. It's not important for protoplanetary disks, because after collisions, particles are always coupling again to the gas, speeding up. Anyway, so that's something in between. And then we get the 100% dissipation. So the gliders just stick to each other. And that's the onset of aggregation, if you want so. So if you deal about collisional growth of aggregates, then it's this kind of thing. It's sticking and starting to grow aggregates. So from the physical point of view, if you're dealing with dust particles or whatever, colliding and sticking together, or not perfectly sticking, the question is, where's the kinetic energy going? And you have a few things you can do there. You either, if you have dust particles, you can create bonds that in the first place sets free energy, but if you then transport this energy in your particles by some waves with some damping, you can get rid of this energy, or you can break bonds. For this, you instantly need energy. So what that means, for example, if you have two particles with a connection here, and this is a lower surface than if you separate this. So for example, if you would roll each other, you would have to break this, make a new contact here, but that can dissipate energy. Or if you have rough surfaces and you slide over each other, that dissipates energy because on a microscopic scale, your atoms are kind of moving and having friction. So all these details are out there, and someone thought about how to work out numbers there. In the end, what is often important for me is that you end up with some kind of critical velocities. For example, the sticking velocity. That is, if you have a particle impacting a wall or another particle, so what is the maximum velocity you can have up to which the particle is still sticking to the wall? If it's higher, you would have bouncing or fragmentation. And for example, you can come up with something like this. So here's the surface energy, which depends on the material or how the surface is made of. If there's water layers on it, these things, elasticity and density. That's something you can not play around too much, but you can certainly play a lot around with particle size. So size is very important in this whole thing. So important parameters, particle size. Simple view is, sure. Of the particle, yes, yes. So particle size, everyone knows that. Dust sticks perfectly, small particles. Sand doesn't stick so well, at least not usually. Try to throw some hand of sand on the wall, it's usually not sticking there. At least that's my experience. Not that I'm always throwing sand against the wall. Anyway, then collision velocities are certainly important. If it's too fast, it's not sticking. And material is also something that is important. So let's start with the later ones, materials. We mostly work with silicates because that's a whole bunch of material on Mars in protoplanetary disks and so, and that's the easiest thing to do. Just some quartz, olivines, basalt, something like that. But there are other materials. Here, for example, we tried an experiment with CO2 ice. I know CO2 is also on Mars, but that doesn't mean that is immediately relevant for this because I don't think you have a lot of small particles there, but that is something one can discuss. But also here you see that particles impacting a surface can stick, can bounce off and fragment. So you always get the same kind of things with these. My colleagues, Miriam and Jens, also did a few papers on this. I think the general outcome is that CO2 does not behave so much different from silicates, if I want to summarize this. Another thing that is important, not sure I've shown you this, organics. So, you know, there's the idea that the moon is made of cheese. Yes. So if you want to show this, then you have to show that you can have a collision at high speed and still sticking. So this is some cheese. Someone told me I have to be careful what kind of cheese I choose if I'm talking about it in Belgium, but that's just some cheese which looks like the moon. So there will be an impact coming from the right with some other cheese, and you see it sticking at 50, 60 meters per second. So that's kind of the proof that the moon is made from cheese. No, that's the funny part. It's not really only funny because in protoplanetary disk, for example, you have some phases where you expect some organic matter to be in a right range that it's pretty sticky. Well, otherwise, yeah, we just made this for fun. And we ate it afterwards, and so no one was harmed, and all these disclaimers. Yeah, so speaking generally, this is from a planet formations thing, but that also applies for other collision scenarios. You start with particles, you can initially grow, you end up at a velocity where you only have bouncing. If you could make it to higher speeds, you get this fragmentation. And then there are a couple of processes which might help you kind of shifting these boundaries in velocities or so. Okay, then the next point is if I'm saying collision aggregates grow, do aggregates really look like this? Do they look different? That's another story then. And if I summarize this, there are, I would say, two extremes. The one thing is the left here, that's kind of a fractal growth, meaning that you usually have clusters of the same size. They collide and hit and stick. So at the first contact point, they just make a rigid connection. And that means the larger they grow, the fluffier they grow. So that's the one extreme. At one point, if they're big enough, and again, you have enough collisional energy, then you can do this rolling over contacts or sliding. That means you can kind of try to compact these things. So you can restructure them, and they're getting a bit more compact. And the real other extreme is this here. You can either make this by a lot of restructuring, or you can have a different process that you don't grow by two aggregates of the same size, but having one aggregate and always adding individual particles. So that would be a particle cluster aggregation then. So these are kind of the two different things. This is actually not a dust thing. That's from a recent sounding rocket experiment. These are all millimeter grains in a few centimeter aggregates sticking together due to charge. Different story. Okay, so that's the view I would have if you just have aggregation by collisions. You start out with fractal growth, get restructuring, eventually have your complex things. And that is important in the description of these things. For one thing, if you have a compact one, you can just describe it with a porosity or a filling factor. Filling factor is the volume of the solid grains over the total volume. Yeah. And porosity is just 1 minus the filling factor. So both are used in the literature. That's easy. So independent of the size, you could always kind of plug a filling factor to this. And Tim was talking about aggregates yesterday. So if it's a 50% or 50 something, that would be a very compact one, or 80 or 90% porosity, which would be more open structures. It would still look like such a compact thing. So this is all in the range of possibilities. On the other side, if you take this fractal, fractal means that your mass of the aggregate is not increasing with the size to the third power, but something else, a fractal dimension, which is usually not a whole number, but something like 1.8 or whatever. So something usually smaller than 2. If it's Brownian motion driven, it can initially be 1.5 or something like that. Point here is you cannot pin a porosity or filling factor to these things, at least not independent of size, because as these things grow, they get more and more open space. So if you would put a filling factor to this, it would decrease with size. In any case, what this is important for is, so you have a mass which is depending on some size, power, and the cross sections. And this is different for these two aggregates. So this is important for the optical properties. So if you really want to deal with aggregates, it matters if you have a CCA or a complex thing. And it's important for aerodynamics because the mass, for example, in sedimentation matters for the speed, and the cross-section for the force, gravity, and the cross-section would be more important for the particle drag. So that means, for example, here in the compact case, the ratio increases with size. That means larger hailstones are falling faster than smaller ones, which is not good. On the other side, if you have something like snowflakes, which are more fractal-like, and if on one winter day, winter coming soon, winter is coming, different story. If you observe the snow, it doesn't matter if it's a small snowflake or a big one. They all kind of fall with similar speeds, well, more or less. Okay, so why is that important for the Martian atmosphere? Kind of going to some applications. So small micrometer aggregates can be suspended against gravity. The morphology of the aggregates is important. We heard this yesterday from Olga and Julia. Shape matters. If just grown within the atmosphere, I would expect them to be CCAs. Probably the density in the Martian atmosphere is not large enough that most of it is grown. I don't know. Then they would be fractal. If it's more like evolved from condensation and evaporation and all this stuff. Talked to Jem yesterday about this water stuff which can kind of collect particles and sediment down. It might be different, or if it's kind of emitted as fragmentation from saltation events, then it's a different kind, and it's not grown by collisions, but it's a kind of a fragmentation process. And then that might also be different. And we heard from Tim yesterday that these might be more like the compact parts. Okay, fragmentation of grains. I think that is something John is talking about. It's not the fragmentation, but the wind stuff. So I'm not talking about any wind here. But if you're on some surface and you have saltation things, you always have these impacts and particles which are set free into suspension. So talking about fragmentation, here is again one from my other part of research, more planet formation. So this is a centimeter, fused 2 centimeter, 3 centimeter diameter thing consisting of micrometer SiO2 grains colliding with a few meters per second, 1 meter per second. Two things of this, and you see in the end something is sticking here, but that's not the important point here. You get some fragment cloud, and you see there are a couple of big ones and a lot of smaller ones. And if you do some size distribution with these things, usually what you end up with is that you have some power law, usually power laws. I don't really think, I think there are some explanations for this, but there's not always a good one. But you often end up with power laws with fewer big particles and a lot of small particles. However, if you have this, you need some kind of cutoff at the lower particle size. Otherwise, you would have infinite number of mass in your particles, and that cannot be. So there's always some kind of cutoff. And if you go to some theoretical things, don't look too much into this. I think this plot is too crowded. I just took it from this paper here. What this is, impact of 20 of small aggregates. So different aggregates. So this curve here is for aggregates. If I take, for example, something like 200 micrometer aggregate, colliding it at 20 meters per second, then the smallest particle should be here a few microns. Now, if that is already the case, then if we would have something like an impact, which Tim simulated with a meter per second, can we really explain the micrometer grains? So that was the justification for doing these experiments in Roadmap. And if you do so actually you should kind of increase here, but then if you're somewhere at this cutoff point, and then you decrease again with your particle size, and that is what Tim showed us yesterday. Okay, the other thing that is not straightforward to deduce from this fragmentation stuff is what your aggregates look like. Are they open porous? Can you find these CCA kind of things? And that's also something we didn't know. At least I had no real clue. So that's another thing Tim told us yesterday, that this is more compact. Okay, now let's move on. This were just simple collisions, sticking, bouncing, fragmentation. What if we could add some energy, internal energy to this process? And let's see what I mean with this is, I have this nice toy. Hope it works. So just put some more energy into this, and if you drop this, it's kind of hopping higher than the initial height. So obviously, in the collision, some energy is released. Can we find something like that in nature as well? And yes, yesterday there were already some words about dust devils and non-dusty dust devils. One idea how a dust devil could pick up dust is from a pressure difference. So this is a vortex. I'm not an aerodynamic expert in this, but knowing that if you have this vortex, there's a pressure minimum in the center. And if you measure this on Mars, Mars with a few hundred Pascal, overall pressure, the difference from the center is a few Pascal. And the question is, if you have a few Pascal in the minimum and then it moves over the ground and you have a few Pascal more below the surface, you will have some gas flow. Is the drag enough? Or can in a more compactified surface, can you increase the pressure so much that you have some support for this layer that it can kind of erupt just due to the pressure difference. And we did some experiments a few years ago where we actually had a setup where we had a thin layer of dust particles. Well, dust, they were about 50 microns in size, and put a few Pascal difference on this, and the outcome was that you would need about 2 Pascal difference to initiate some particle ejections. But I was talking about collisions. So here is an experiment from this. So you see a particle kind of being ejected, impacting here, and the whole ground is under tension. So it kind of launches an avalanche of more particles. So collision is not just one particle and the other and energy conservation, but if you already have some tension on your layer, then that can kind of multiply your output. Another thing comes here. So with the dust devil, that's again kind of simple physics, just an overpressure under the surface. Now it's getting a bit more complex. So this, I'm talking about the next couple of minutes, is called thermal creep. It's not thermal, I think there are 2 thermal creeps on Mars. Some people call it thermal creep if you're on a slope and the thermal waves go through this and you have some slow particle motion over months or years or whatever. That's not what I mean. But if I'm talking about thermal creep, that's some gas motion through the porous space. So what that makes, this is very nicely visualized here, is this is dust aggregate. So the whole particles here are on the order of 10 microns or so. So the whole thing here is, I guess, 300 microns, so roughly half a millimeter, say. That was on a heater before, so it was a few hundred degrees hot. And then we kind of just kicked it off the heater and it's dropping. So it's in free fall, and we observe this with 25,000 frames per second. The surrounding pressure is a few hundred pascals, so that's comparable to Mars. And what happens if it's dropping? That should work now. It's just exploding on itself. And yeah, so obviously what happens is that if these things is hot initially and it cools on the outside, but it's still warm in the inside, there will be some gas flow from the warm outside to the inside until the overpressure is enough to explode this. And so this happens on size scales of sub-millimeter. We can also use this as a technical tool. So these are dust aggregates, same thing again. Now they're on a heater at the same pressure of a few millibars, meaning if this whole thing works, then it should kind of suck gas from the cold top to the hot bottom. And that should create some hovercraft air cushion, and these things should levitate. And that is what happens. So here is, these are millimeter dust aggregates, again, consisting of micrometer grains. And they're just levitating on this hot surface, fraction of a millimeter in height. And then in this case, we can again study collisions. This, for example, is just at this bouncing transition. So sometimes they stick together for a while, but the connections are very weak so that the next connection can destroy this again. That's kind of called bouncing barrier and planet formation. Yeah. So the thing how this works, I still think it's called thermal creep because it's creepy. You cannot really make a good explanation on this. You can put in equations and numbers and it works out. But generally, the idea is if you would have 2 reservoirs, a warm one and a cold one, and you would want to have the same pressure in both of them, you would just punch a hole in the center because then the pressure would equilibrate and you would have the same pressure on both sides. That's normal thing, you know. But if you decrease this size here of this connection, and if you decrease this to a size that it's on the order of the mean free path of the gas molecules, then it doesn't work that way any longer. Then you have this thermal creep, gas flow, and it's going from cold to the warm side. So at this, if you have no collisions here, you can do some flow rates from ideal gas things, and then you really get the result that more particles are moving in this direction. And that means that you get an overpressure at the warm side. So that's the underlying thing here. It's not, I didn't invent this thing. Actually, that goes back to the times of Knudsen in the early 20th century. He connected small and big tubes and heated the connections, and he could have a pressure increase on one side over the other by a factor of 10. So it's not some minute detail. And as you just saw, this aggregate's exploding. So that's really something which is working on under Martian pressure. And actually, Mars is the only place in the solar system where this works naturally in some environment. We don't have this in the soil on Earth because the mean free path is only 60 nanometers or so. You don't notice this. So that is something which has to be kept in mind. Mars is different in this respect. Okay, we did a couple of experiments with dust particles there to see how the pore space behaves. So the pore space is kind of is the place where this thermal creep happens, but you can have large pores, small pores. So this is complex. However, in the end, you can still simulate the whole thing by assuming you have some tubes of pore diameter in there, and then you can work out mass flows and pressures with this simple model, at least if your dust bed, particle bed is not too complex. Yep. Okay, this is again how it works. Anyway, not going through all of this. How this can work on Mars is that you usually heat the surface by illumination. So sun is shining on Mars, it seems. And what that means is that, for example, if you're having your particle bed here and it's illuminated from the top, radiation is somehow entering a bit below the surface as well. So that's again where radiative properties of your particles are important. But at the same time, the top can cool by thermal radiation. So in the end, what this turns out is that you have some temperature gradient here in the ground. It's cold at the very bottom. It's getting warmer upwards. And then you have a region which is having a more of a flat temperature profile. And the flat temperature profile means that you have no thermal creep there in the top layer, but you have it below. So this here, actually, the thermal creep, it doesn't need any pressure difference. It's just the creep which is doing the flow. But at this position, it cannot go further. So if you want to maintain this flow, you have to increase the pressure here to get over through this last layer. And that means that you have some overpressure just a few millimeters below the ground. And then you back again at this. This is just the overpressure thing, but that means that you can have some support for your particles. Okay, if you do this really with light, here are some experiments from the drop tower. This is a cloud of particles that is just illuminated, and that's kind of the other side of this effect. So particles in the light are moving away from the light. That's called photophoresis, but it's essentially the same thing because the gas around this particle moves from the cold to the warm side. So from upwards, that means if you want to have momentum conservation, the particle has to move away from the light. If you do it really with a surface that's illuminated, so that's again also in the drop tower. If I start this movie, then there is a particle bed illuminated in the center, and it's just spitting out particles all the time. However, this is at a few kilowatts per square meter, so it typically only works continuously at 4 or 5 kilowatts per square meter. So that's way beyond Earth or solar constant and way beyond Mars. But that runs all the time, which is funny. And you don't need anything else, so no impactor or so, that would just work. And if the light is turned off, it's even increased because then the temperature structure changes in a way that you get more overpressure under the ground. Okay, so this is more as a visualization. If you really trace the particles here, they come up in the center, but falling back at the site. Just recall that this is in a drop tower, there's no gravity, so they follow kind of a gas flow from the shadowed region in the illuminated region and back to the shadow. So I think this is some effect that could work on Mars, kind of getting the gas down in the shadow and up again in the sunlight. Okay, this is just another confirmation of this. Again, a different kind of experiment called diffusive wave spectroscopy. Not sure you heard about this. I had a colleague who thought about this would be a good idea to do this. I didn't hear about this before, and we only did 2 experiments with that actually. Idea is you look at a particle bed from the side with having a laser illuminated the whole thing. And that means you get some speckle patterns. And this speckle pattern changes if your particles move a bit. And this is so sensitive that you can track changes of the particles on a nanometer scale. So if you do this whole effect thing here with the illumination, you should get some particle motion on top. And then there's this pressure minimum. And if it works, particles should also move downwards. And that's essentially what you see here. So 2 millimeter, there's little movement, there's a lot movement on top. And if you had the right pressure regime, so here 5 millibars, Martian pressure thing, you get some motion at the bottom as well. If you had higher pressure, there's no motion. Again, that means Mars is special, or millibar pressure is special with respect to this. And here's just this pressure regime again, where these effects happen. This is all perfectly set on Mars. In this respect, if you like this effect, Mars is really a cool place to study these things, I guess. Okay, but I just told you that you need a few kilowatts per square meter to really ignite this on its own. Then a couple of years, Frederick Schmidt suggested that this effect might help explaining this, this low inclination on some slopes, this recurring slope lineae, which occur annually and vanish again. So he proposed this thermal creep might work this way. And we developed an experiment over the last few years that we could test this really under Martian gravity, which should change things, and under Martian illumination, under Martian pressure. So to see if this inclination angle really depends on the illumination and this stuff. And to do so, this is the experiment. This is something built for a parabolic flight. So the whole thing is a centrifuge so that we can put it at 0 gravity, spin it up to Martian gravity. If it's static, we don't have to worry about Coriolis so much. We have chambers here. These gondolas are kind of going outwards to adjust to the gravity. This chamber here can be inclined, so putting on slopes. It's a vacuum chamber to get the pressure right. We have a illumination here with a lamp, which can do about 1 point something kilowatt per square meter. And we have a dust container here, which can be shaken to make it even and put this all together. So it's not yet cold temperature. We currently use just air, no CO2, but it's already kind of very complex. So it really took us a lot of development to do this. And we recently, in May, put this in a parabolic flight for the first time. I like to talk about parabolic flights. This is the experiment in the plane. You see some money went into this from Roadmap. So there's a sticker, Roadmap. The stickers are only on the back side so that this view here is free from everything. It's not has nothing to do with this symbol here that Roadmap is just close by. Which is a freaky one, but this thing is rotating. We even have a Mars thing on top. And the whole thing is supposed to work under microgravity. Okay, this flights. This is a nice movie. Sounds. So that's the plane. It's pulling up. That means that you have 20 seconds where you're hypergravity, 1.8 G. It's hard to move. Very epic music. You should not move your head too much. That's the dangerous phase there. Otherwise, well, you have these bags which you can fill, and there are all nice people on board. They give you a new one if you fill it. Then you have this parabolic thing with 20 seconds of microgravity, and then the whole plane drops down again. And eventually, when it pulls out, it's again 20 seconds about microgravity. That's kind of Jurassic Park, right? Anyway, so that is essentially 1 minute, 20 minutes of fun, 40 minutes of work. Then the whole thing kind of moves again 2 minutes in straight flight. And then it does this again, and it does this 31 times in a row. So if you can take this, that's the best roller coaster in the world. So that's me. That's actually also a thermal creep experiment from earlier times. So that's just the proof that I was on board. Actually, the experiment this time was called OWL, so there was an OWL. This is also a thermal creep experiment from the past. This is just to show you that Anna actually was there and she was laughing all the time. So there are two kind of people on these flights. Either you like it or you don't like it. And if you don't like it, you only fly once. I had to convert this. Actually, I started the movie only at the microgravity phase, and now you see the whole thing. So that's the 2G phase. Everyone is kind of trying not to move too much. Everyone has its own strategy of working with these 2G phases. 30, that means kind of the inclination, and then comes 40, and then it's kind of injection. I think she's really selling it, and Jens is still doing some work. So it's really fun. Okay. Okay, so this is now the experiment Scarlet, which is rotating thing. Well, really important movie doesn't work. QuickTime. Okay, I had to convert it yesterday from key Apple Keynote to this thing. But anyway, so what you would have seen doesn't matter. It's another thing anyway. So these are the gondolas, and once you're at hyper G, they're a bit more tight to the whole setup, and at 0G, it kind of flaps outwards, doing what you're supposed to do. And so this is a first result of this. So this is an illumination spot. Actually, that is when the light was turned out. And this, for example, is then a particle motion moving downwards. To the left is downwards in this event. So you have kind of the slope over time. This is the residual gravity, so it's close to Martian values. And what you see here actually is that if you don't have the light on, these particle events only start at about 20 degrees. The particle bed, obviously by all this kind of shaking, is a bit compacted. And it's not like the huge slides we see, but it's more like individual particle motions. Anyway, without light, they only start at about 20 degrees. And if you have the lights turned on, you can go down 10 degrees lower or so. So I think that might really be something important for Mars. And this is actually at Martian flux, so a few hundred watts per square meter, no longer this few kilowatts or so. Yeah. Okay. Yes. Another thing, if you do collisions, eventually you start thinking about tribocharging or so. That's not what we did initially. When I worked on planet formation, where you have these dark protoplanetary disks, I know some 30 years ago, it was always a good question of people, do you consider charges? And the answer was always, well, these disks they are dark, there's no ionizing radiation in the center, there's no charge. And it's only, I think, couple of years that I realized that charges are really important if you have these collisions of particles. So for example, we had a few projects. It's a couple of years, that was Game of Thrones times. So we had a project called Lannister and another one which was called Dark. Anyway, It's the little fun we have in life. As the experiments were in the drop tower, here we did some shaking of grains. Initially, it was sub-millimeter particles, spherical particles, so that we knew the mass perfectly. Did some charging in these collisions, then they were ejected in microgravity. We could observe the particle motion, and to the left and right there are some electrodes, so we can make a plate capacitor, and we know the electric field and can get the charge of the particles. And this experiments, for example, that's how it looks. Particles are coming from the right. Depending on their charge, they're moving downwards or upwards, and we can do a lot of things with them. For example, we can get the charge distribution. That's kind of a double exponential thing. A lot of them are uncharged, net uncharged. A few of them carry a lot of charge. So what you can do with this is, again, important, coming back to collisions. So on the right, this is from a small homemade drop tower, Lee et al., Heinrich Jäger group in Chicago. They did this, published this in 2015, some particles, and you see that they kind of built aggregates there due to the charges. Yep. We did the same in the drop tower, and if you, for example, follow these two particles here, it's they collide. It's not quite elastic, so they find themselves again until eventually they stick to each other. And you can observe these things then with dimers, building a quadru, whatever you call this, and growing to larger aggregates. So kind of having individual particles and eventually growing ever larger. And actually, the largest things we do are now the centimeter things. So again, here is the chamber is about 5 centimeters. That were the preparations for the sounding rocket experiment. This was not shaken before, so it's uncharged. You don't grow much. This was charged by shaking before, but it's at 1 bar atmosphere. And this was also shaken before at low pressure, 0.2 millibars. And actually, if you do this at low pressure, it usually works much better. If you observe this here, it kind of looks like a bed. So charges grow beds, I think is the message. I can never be serious. Anyway, so this means that you can really grow large aggregates with these things. What does that mean if you're having collisions of these aggregates? So this is, for example, an aggregate made of 80 micron basalt particles. That was kind of pre-shaken and formed. And if you see this colliding with, okay, that's again one of the movies didn't work. So I describe what you would have seen. This thing just hits the wall and only breaks in 2 or 3 parts. If it would not be charged with this particle grain size, it would be splattered all over. But its charging makes it much more stable. Another thing we could observe in the drop tower is if you have these aggregates impacting, they can kind of be disassembled if it's fast enough. And then you can get in the electric field the individual charges of the particles. Sometimes you find these things, negative, positives. Looks okay, that's what you would expect. But sometimes you also find this, just positive particles in a stable aggregate. How can that be? Obviously, net charge is not everything to the whole story. You need higher order things. And in fact, dipoles, multipoles, our view of these particles currently is that you have a very patchy surface. And that can, even if your particles would be net charged, you can still have a strong interaction between close particles because Coulomb works 1 over R. If they're close by, it doesn't matter that the whole thing is neutral. You can still kind of stick them very well together. And we did some experiment, for example, in the drop tower where you see these dimers oscillating. And that gives you a dipole moment. And with the net charges, you cannot explain these dipole moments, but you need something like that. There's another experiment with a trap. You probably saw Jonas' poster on the trap. Here we used it for something different. We had some aggregate in there and a field attached to it. And this thing kind of is oscillating. We can get this oscillation. And from this oscillation, we can get It depends on the field. That gives you the kind of dipole moment. And then you see, for example, larger aggregates have larger dipole moments, nothing special. But if you don't shake the sample before, it's smaller. If you shake it, it's larger. So that is some information you can get of the next level. It's not easy to get the really complex charge distribution, but that works out. So how to destroy these things? That's on Jonas' poster, but you didn't see a movie to this. So I have a movie here. These are millimeter particles in there. They're rotating in the trap. Didn't work. Bummer. Okay, so it's essentially now only a static image, but you would have seen it rotating and the particles got lost over time from this aggregate. And that kind of gives you the force with which it is it. I don't think it works. It's probably, again, a quick time thing. Doesn't matter. So if we see each other in the future, you still have the chance to see this movie. And it's new. That gives you the force, and the force is much stronger than just adhesive would do. So that's one way to quantify these things. Another thing which goes along with these collisions and charging, that is actually something that Laurent did a couple of years ago already. So again, this is a box where we shake particles. We put this again under pressure of millibars. But now the chamber is dark, and we just watch into this dark chamber for a while, and you see it glowing. For one thing, it's cool. It's always cool if something is glowing. On the other side, that means that you have some kind of charges going into the gas phase in this this respect. So, for example, afterwards, if we analyze the collisions in a drop tower, where you have a total charge before a collision and after, it's not conserved. That would be the black line, but it's losing charge. So obviously, tribocharging is not only about the grain surfaces, but you can eject some of the charges into your surroundings. And I think that might also be important for atmospheres. I think it's important for protoplanetary disk, which you can ionize this way. It might be important for even for Earth's atmosphere, because if you have volcanic eruptions and collisions, it's not just creating large electric fields by tribocharged separated grains, but you can do it on a much smaller scale. You can do this in dust storms and all this, and I think a lot of these charges in the atmosphere might come from such collisions. Now, this so far was always millimeter, submillimeter grains. We recently kind of turned to dust aggregates again. You see what these collisions do. You have much more deviations from charge conservation in these collisions of these dust aggregates. And this is probably due to the fact that you now have some small fragments again, so it kind of closes the circle to the initial collision thing. And you eject some charged particles already. So having saltations and fragmentation might already kind of put charged particles in your atmospheres. So having tribocharging changes aggregation, can ionize the atmosphere, can shed some charged dust again back into your atmosphere, whatever reason. And I think that's essentially all I wanted to say. Thanks for your listening. Anyone wants to know something?
So, question, when you showed the experiment, when you have this hot aggregate dropping through cooler, you said you had a few hundred Kelvin difference?
I think initially the heater was a few hundred. Actually, yeah.
Play around with different temperature differences to see kind of thresholds
Um,
when you would actually, the difference would be too big so that you would actually.
yeah, I see. Know what you mean. For example, for this levitation thing, I think over this millimeter aggregate, the temperature difference is about 20 K or so, and that still levitates things. In this recent Scarlet experiments, when we turn out the light, you have a temperature difference cooling by about 5 Kelvin, and the things start to move. So certainly there is this temperature dependence. I'm not sure you can really plug a certain number to it. That depends on the gradient you create in this aggregate to make this.
From you say a few kelvins difference is already something that would impact some aggregate. Okay.
Yeah, that depends on the length scales you're talking about. If it's, I don't know, centimeters or so, then you need more. But if you're only talking about a millimeter layer or so, it doesn't need a few kelvins, and a fraction of a Kelvin would be enough.
Yes, so we have a question from Luca online. Could thermal creep account for some of the background dust opacity on Mars together with the contribution of dust devils?
Yes, that's what we suggested. But well, on a flat surface, I don't think it's emitting on itself, but it would kind of reduce, I don't know, threshold wind velocities. That's one thing we did in the past, that it can decrease this by 10, 20% at least. So it can support the whole thing. And if you have this slope activity, so I think it's in there as a supporting actor for all the other mechanisms. Yeah. I work on this, so I would always say yes.
Have you ever tested how is the effect of the monomer shape in this growing process of large particles? Instead of spherical particles, you have a larger contact surface. Will that affect or not?
It has an effect. It has an effect on the if you build these fluffy surfaces, for example, if you do this with irregular particles, the filling factor is not so high, so it's getting more fluffy. So it's not, because spheres can rearrange much better than the irregular particles, so that changes things.
But I mean, in these stellar disks, are there any evidence for spherical monomers in there, or just to facilitate the experiment, you are using spheres, or?
Yeah, well, with spheres, it's always easy because then you can compare this to models and all this stuff. But for example, for the recent, we did some recent experiments where we milled meteorite dust and compacted it again to cylinders, do some tensile strength measurements that were irregular grains. And then the forces were measured for these. So I don't expect spherical particles necessarily in these disks. I mean, chondrules, which are millimeter particles, are spherical, but otherwise it's rather irregular, and that will change things a bit, shifting threshold things around. But I don't think that is drastically. So I would, for example, more think if you have a 100 nanometer grain or a 10 micrometer grain would make more difference than playing around with shape.
About the thermal creep explanation, so you have, I'm not sure I get it. You have this warm reservoir of particles, the cold one, the small holes, and you were saying the more cold goes, the colder particles go to the warm side, and my first reaction was, but I would expect it be more hectic on the warm side. You would get more particles from the warm going to the cold.
Yes, this is not intuitive. It's counterintuitive, actually, I think. But
I don't know if I'm confused.
It's not. It's completely normal if you're confused. Yes.
I'm missing some, because you have more particles on the cold side, so their chance of moving to the.
Yeah, but if you put in, I think the collision rate with the surface of this hole, and you take your density you have on the cold part and your velocity with the thermal temperature there, and doing a balance on both sides, then you see that it's more particles hitting the cold area than the warm area. As I said, I don't have a real good visualization for this, so it is counterintuitive, but it is there.
Thanks.